So I'd like to welcome everyone to our workshop today. This is a repeat of presentation that we were able to make up at ALA conference, the annual conference in Louisville, Kentucky on September the 8th. So this step-by-step approach is what we're doing, and we're going to recap some of the slides we had in section 1 and then also cover and add to that section 2 of the presentation. So let's go ahead and get started. And so first of all, we'll begin. So as we discussed earlier, the difference between relative and absolute photometry. Relative photometry, as we discussed, is the measurement of photometric quantities of light product, which can be scaled. And so in a laboratory, the ballast factor is 1.0, so that gives you a certain driving performance, a certain light output, a certain associated wattage. And so by being scaled, different ballast factors can be used. Lower than 1.0 would be 0.88, which is kind of like a normal fluorescent ballast factor. 0.78 was low energy. And then all the way up to 1.18 is a higher light output. So it can be scaled. And then the same ballast can be used, whether, let's say if it's a 4-foot tube, you could have a full wattage 32-watt lamp, 30-watt lamp, 28-watt lamp, and a 25-watt lamp. So all of those could be used on that one ballast. So it can be scaled up and down. And so another characteristic about relative photometry is you have a light source, and you take those readings of just the light source in isolation, and then you have a measurement of the whole luminaire output. And so what happens is you can then calculate the efficiency of the luminaire, and then the difference in those two is the luminaire efficiency factor, or LEF. So if you have 100% of the light coming out of the lamps or the LEDs, and then a portion of that is that would be LED lamps. And then you have a portion of that blocked or doesn't come out. So let's say if only 80% comes out, then the luminaire efficiency factor would be 20%, because that would be blocked. Or another way to state that, actually on the cut sheet, would be 0.8. So that means 20% is blocked. And then, so relative photometry is basically is presented showing the lumen output of the lamp, again broken away, as well as the output of the luminaire. So that's in a relative photometry report. And this is very common, what we use for our traditional light sources: incandescent, fluorescent, HID, etc. Now, the difference is absolute photometry. When we think about that, we think about LED. So the entire luminaire goes onto the device to make those measurements. No adjustments can be made. So it is what it is. There's no scaling involved. So the luminaire output is specifically to that fixture or that luminaire. And so there is no concept of the lamp lumens and luminaire lumens. It's all just lumens. And then the luminaire efficiency factor is equal to 100%, because that's what absolute photometry is. And so the values are expressed in candelas or candle power. And this is again used for LED luminaires. So you've got your relative photometry for traditional light sources. The lamp and the fixtures are broken out, and some of the light you have a luminaire efficiency factor, which is how much light is actually coming out of the luminaire. Use, again, traditional light sources. Absolute photometry is LED. So what is included in a photometric report? Well, we talked about the general luminaire description and characteristics. Candle power. What is candle power? It's intensity. And luminous flux. So when you hear the word flux, that's going to be measured in lumens. So those are two kind of like technical terms that you'll hear on a photometric report or see, but that's what that means. Is candle power is the intensity. What is the intensity of the beam, like a spotlight versus a floodlight? and lumens is sometimes expressed as what is the luminous flux. Then you have your lamp and luminaire efficacy, or you have your lumens per watt, kind of like car or miles per gallon. How far can you go, or how much light can you get per watt of energy? Color rendering, CRI, color rendering index. How do the colors appear under the light source as compared to a reference source of 100, such as incandescent or daylight? And that's been around for a long time. And then the other one that goes with that is CCT. That stands for correlated color temperature. So how warm or how cool is the light source? And then we have spectral distribution measurements. You see that colored curve that goes up and down. That's a spectral power distribution. We'll talk about that a little bit later. And then your chromaticity coordinates, that's your X and Y coordinates on that little banana-shaped curve to the right over there on that graph is what that is. Where does the X and Y fall exactly on that to determine the color? What that report to you. Unified glare rating. So that's a term that we can determine how glary is a particular luminaire. And there's different ratings, and the higher the number, the more glare that you have. And then there's something called coefficient of utilization table. We'll cover that here a little later. What that is the utilization of light once it bounces on the walls and ceiling and floor and so forth and hits the task, how much of that light was actually utilized. And then we also, so far we've been covering the optical characteristics. Now we're going to talk a little bit about electrical characteristics. So that's things like watts, volts, power factor, so forth. Those are also included on a photometric report. So all we're doing right now is just providing a listing of some of the technical terms that you'll run into that will be on a report. A photometric report is kind of like going in and getting a physical exam from your doctor. So what they want to know is everything about you from your top of your head to the bottom of your toes. And so they can really find out exactly what is going on and how everything works. And so the same thing is true with a photometric report, because all the aspects of light that are involved, we want to know about what that is. And so that's what a photometric report tells you. So it's a lot of information. We didn't cover everything, but gives you a really good idea of what a photometric report is. Now, this is an idea, gives you an idea of what are some of the categories that we talked about before. So the first one is all the definitions and data that you'll see, the name of the luminaire, what's the wattage, what is some of the characteristics, who's the manufacturer, so forth, up top. Then you go to the next characteristics and you'll see some lumens, luminaire efficiency, the total luminaire watts, the ballast factor, the CIE type, which we'll cover later today. So some of those things that you'll see that ballast factor is 1.0, so that's in a laboratory. And then you'll see some additional things. The next category is something called spacing criterion. So this is how far can you space from one luminaire to the next and still have good uniformity. And so we'll talk about how that's calculated later. And then we'll go into some of the measurements. How long is the luminaire? How wide is it? And so forth. What is the measurements? Just to give you an idea. And then the spacing criteria, let's drill a little bit more into this. So the spacing criteria is from the center of one luminaire to the center of the other luminaire in feet. And so the mounting height is from the bottom of the luminaire to the horizontal work plane. Okay, so we will typically have a spacing criteria, or sometimes it's called spacing to mounting height. There is one more aspect to spacing criteria, a third one that we sometimes use, but the most prominent two that we use is the spacing lengthwise and widthwise. So how does this work? So let's say if the maximum spacing, fixture spacing, is the spacing criteria times the mounting height. So let's look at an example. So here's a high bay luminaire. So you say, what is the maximum fixture spacing, or the SC, is equal to 1.4. So on a specification sheet or in a photometric report, you will be given this 1.4, and the mounting height is 16 feet from the bottom of the fixture to the work plane. So you just simply multiply those two things together, and what you get is 1.4 times 16 equals the 22.4 feet is the maximum spacing they allow between this particular situation for what we call good uniformity, reasonably good uniformity. So that's what that is. Very, very common, very important thing that you need to know about how to read that, what that means. Now, let's go move over a little discussion of color. So the color evaluation samples, CES, of the chromaticity comparisons. So chromaticity is nothing more than just the color of the particular color or hue that you're talking about, and also the saturation, just the characteristics. That's what we call chromaticity. So the hue or the color, and then also we measure the shift from a reference source to the particular source that you're talking about. You see all these dots over here. So the reference source is the blue dots, and the red one is the test source. They say, well, I've got the 4 quadrants there, but really can't really tell a whole lot from that. And so what we do, we'll show you how we actually look at this with another graph here in just a minute. But with this TM30, which stands for Technical Memorandum number 30 by the IES, we look at 99 colors. With CRI, we only look at 8 colors. But in the better, newer metric, we use TM30, and it's 99 colors. And we calculate the color difference in each pair. And what I mean by pair is the reference source and the test source compared. So let's take a little closer look at this, and you'll see what we're doing is taking those, the chromaticity comparison in those particular dots, and we're moving those over to what we call a color vector graphic. And all we're doing is connecting those dots. And again, the reference source is the blue line. That's the perfect comparison reference, versus the shift in color to the red, which is the test source. So what you'll be able to see is you see the graph, and we'll start up in the upper left, and you'll see you see green, and then coming straight down you see blue, you'll see purple, and you'll see some brownish orange red up in the right corner. So this is the shift. So you look at all the different quadrants as it shifts around, and depending on where that is, you can tell what the shift is. So here is our red, which is our test source. And then, so in this case, if we see this area right here, then that's an increase in saturation of that particular color compared to the reference source, because it goes beyond that blue line. Okay. And then here is a decrease in saturation because it's going away from the saturated color of the pink and the reddish color over on the right there toward the center. So the center is more of a white light. So we're decreasing in saturation. Okay. So that's a little bit about TM30. The US version of that is 2020. And it quantifies 2 metrics. So one is color fidelity. So fidelity, think about fidelity like CRI. So fidelity, we're measuring 99 colors with TM30, but with CRI, we're measuring 8 colors. And again, fidelity is how do the colors look under the light. The second one, however, is new, relatively, and that's called gamut. And again, another definition for that is saturation. So, say, well, gosh, we don't really, do we really need all this? Why are we moving away from CRI? Why not just stay with CRI? Because it's simple and I can understand it. Well, the bottom line is, yes, it's an old metric. It came out in the 1960s, early 60s, been around for a long time. They served us well, but it's just not as accurate as the newer metrics. So no matter what, how good a shape your antique collector car is in, let's use a Mustang, for instance, a 1967 Mustang Fastback is a pretty cool car, but you know what? It's still a 1967 car. It's got plenty of age on it. Think of all the advancements that we've made in automobiles since then. So we were making also advancements in color. So let's test this out. And let's see if I can convince you and give you an example of why this is good. So in this first slide that we're looking at, what we're going to do is we're going to hold the gamut steady, and we're going to compare the fidelity. Again, think of it as CRI. Look at the left, top left, 65, versus the bottom right is a 95. So, and we're holding that gamut steady. That's the saturation of the color, no change. And you look at the left picture and the right picture, you don't see a lot of change, do you? No. Now, if we consider saturation or the gamut side, so let's look at that now. So now we're going to look at the fidelity, where we're holding the fidelity constant and the gamut changes, or the saturation. All right, so let's look at this. This is the 65 fidelity, 80 gamut, and now we're 65 fidelity and 120 gamut. This is where our color preferences come in. So just look at the huge difference this makes, right? So look at the apple on the left, the apple on the right. Look at the orange and compare those two. Not a whole lot of difference in the yellow, the green, the blue, or over on the right, you see that red. It's a big difference in the red, right? So the warmer colors is a big difference here. So huge gamut makes a huge difference. And the new metric of TM30 allows us to make that comparison a lot better. And it allows specifiers or homeowners or whoever it is to make a choice of what that is that they want. Okay, we're going to switch gears now and go into photometric report. We discussed this, the same thing, and we were in Louisville. This is a mess, right? You look at all these numbers, you say, I have no idea what all this means. So it's a lot of technical data. So what we're going to do, break it down step by step. So the first one we're going to look at is this spacing to mounting height. Remember, we just discussed spacing criteria. I showed you how to calculate that. So you got a 1.3, 1.2 along, and a 1.3 across. So what does that mean? So if you have the along, if you have like a 2x4 frother, let's just say, for instance, the shorter one is the lesser number is always going to be the 2 foot, and the 4 foot is going to be the long one because it's higher and it covers more area, so you get better spacing. So that's kind of how you figure that out. Now let's go over to the next table, which is the luminance summary in candelas per square meter. That's a metric that we use to measure luminance, or what is that? That's brightness or for reflected light. Now let's go over into the table and we'll see the angles. So at 45 degrees, we see along and we see across. These are numbers expressed in candelas per square meter. Okay, so you'll see as it goes from 45 to 75, it changes. So you can see the luminance comparison there with those numbers. Now let's go over here to this candela or candle power distribution summary. So the first thing we'll see is the blue vertical line, and we'll start up here with this angle. We start at 0, and then we go 5, 10, 15, 20, etc. So all this is really just taking this and just raising the angle up. So right below the luminaire is a 0 angle. We call that nadir, N-A-D-I-R. And so as we increase the angle, then we see there's numbers associated to the right. And so you'll see that they go down. As we increase the angle, these numbers go down. Now, that's the vertical side. But we've got another side here, and that's the horizontal side. What this means is if you have your particular light, and let's say instead of going up and down like this, what we're doing is we're going to turn it sideways. So if we turn it to the right, 22.5 degrees, and then we drop down, okay, a certain number of degrees, that is what that number means. So the horizontal means we turn it from left to right and get an angle, and the vertical means up and down variation in angle. So see, all of a sudden, now these numbers mean something because you know how to read this table. So it's not really that difficult once you know what you're talking about. Now let's go down to the bottom, and we're talking about the zonal lumens. So this is all of the flux or the zone, lumens in that zone of a certain angle. So we'll see like 0 to 30, you see a certain number of lumens. And so this happens to be have a lamp in it, like a traditional, maybe fluorescent lamp. So what is the percent at that angle of the lamp lumens? And this, in case in 0 to 30, is 31.19%. And then we go to 0 to 40. Now we increase the percentage and so forth, all the way up to 0 to 90, and you'll see, what is that? 100%. So now you're going from 0 right below the luminaire all the way up to 90, which is horizontal, and all of a sudden now you're including all the light. And then you go from 90 to 180, and what do you see? You see 0. Okay, what does that mean? Well, it means you don't have any uplight. 90 degrees to 180. That's what that is. Okay, and then the total is 100% of the luminaire. And then the last one that we see is efficacy. So we'll see here lumens per watt. How efficient is it, or miles per gallon? That's a lighting term, efficacy. Okay, versus efficiency. Efficacy is lumens per watt, and efficiency is like what percentage of the light is coming out of the luminaire, which we covered earlier. So all of a sudden, we have finished a lot of technical data here, and now when you look at this, you know what this means. Now there's one other part that was on there that we're going to break out, and that is the candela distribution, or the candle power curve. So they give you a curve, which you see on the left side of your screen. They also give you a digital chart on the right side. So same format that we had before that we discussed, the vertical up and down and the horizontal along, which is the 22.5 and 45, etc., which is turning it left to right. So if we read that curve, sometimes that might be hard to read. So you say, I need a number. So in this case, here is nadir. This is right below the luminaire. You see the 0 up there in the digital. The angle is at 0. There's no tilt, no vertical tilt. And so we see 0. Now, if we change the position of that curve, and you see it intersects that line at 45 degrees. So you see 45 on that polar chart there, and you read up, and that's where the arrow starts over on the left side. You're reading 45 degrees, and then it takes you to the right, and you see that chart where you can read exactly what that number is. So sometimes you can easily read one of these candela distribution curves, but they also typically will include the values in a table. like this. Okay. All right. So we've already gone over the vertical. We've already gone over the horizontal. So now we're going to get to a very important, where we left off actually the last time, which is the coefficient of utilization table. This is very, very, very important table. I want everyone to learn today how to use this table. So what this means is I've got light coming out of a luminaire. It bounces and hits the walls, the ceiling, the floor, and eventually a certain amount of light hits the task. So what percentage of that light hits the task? Well, there's certain things we have to consider. We have to consider the amount of spacing and how far is it away, and also the relationship of your walls. How much walls do you have compared to the floor space? So square footage of the wall space compared to square footage of the floor space. So let's take that first in simple terms. So if you have a hallway, you got a lot of wall space in a hall, right? A lot of walls, a lot of footage, a lot of square footage there, compared to a smaller amount of square footage in the floor, in the hallway. Let's take the opposite of that, where you have a large open office. So you've got a lot of floor square footage, and the walls are far apart. So there's much less wall space compared to floor space. All right, so that calculates into something we call RCR, or room cavity ratio, and we'll talk about that more. So let's first learn how to read this chart. So the first thing we're going to do is look at an example. So our example is reflectance is 70, 50, 20, and our RCR, this relationship of the floor space to the wall space, has a value of 4. What is CU? So first of all, we're going to look at our chart, and we see 80, 70, 50, 30. So that's the ceiling reflectance value. A white ceiling typically would be rated around 80, a medium ceiling around 50, and a dark ceiling maybe 30. So we're going to pick 70 for our example. Then we have the wall reflectances, and under each one of the ceiling, we have a 70, a 50, a 30, and a 10. So let's take a look at our example. We've got a 70 on our ceiling. We've got a 50 on our walls. Okay. Now we have a effective floor cavity of 20%. Typically we'll use 0.2 for our calculation on our floor. You can adjust that if the floor is a lot lighter or a lot darker. Typically we don't, but you can. So now we're going to go vertically and look at our room cavity ratio. So the smaller numbers is going to be like that open office. So you're going to be a 0 or maybe a 1, something like that. A hallway may be up around 5 or 6 or 7. So the larger numbers, what that says is all that wall space compared to the floor space eats up light. It just absorbs that light. So therefore, we've got to account for that absorption. And that's what this RCR does with the different values. Okay, so now we've picked our RCR, and we know our example is a 4. So what we do is we read, and all of a sudden we see with the intersection of the 50 and the 4, we see 0.75. What that means is that of the source of light coming out, 25% is trapped, and we only can utilize 75%. That's what that means. Very, very, very important table to understand as far as reading photometrics. So let's take a look and see if we can read this candela distribution curve. What is the candela at 30 degrees? So we see the 0 here, and the answer is 6,000. You see where the curve intersects the graph at 30 degrees, and the answer is 6,000. That's the way we read that. Just what we went through before. Okay, now we're going to go into photometric measurements and test methods. So there are three instruments that we're going to focus on. One, the first one is what we call a Gaudio photometer. It is a device used for the measurement of the light emitted from an object at different angles. Typically, it's going to be a luminaire. Could be a lamp also, but we put luminaires on these, and this is a device where you put it on one end and you spin it, and we'll demonstrate that. The use of gaudiometers has been increasing in recent years with the introduction of LED light sources. Why? Because every single difference in lumen output, you've got to do a new test. You can't vary the lumens like you could with the traditional light source. That's why. So here is a Gaudio photometer, and this is what happens. So you put the luminaire on one end, and then you spin this around, and the light hits that mirror that's spinning and goes to the back of a room, and it captures the data. And this Gaudio photometer, along with a lot of information it gathers to give you a photometric report, it also creates what we call an IES file, or .IES. And those IES files are used to pull it into a lighting software that calculates a lot of measurements for you. And lighting designers use that all the time in their work. But this is a Gaudio photometer. We also use an integrating sphere. So an integrating sphere collects electromagnetic radiation, that's just light, from a source from flux measurement, that's lumens, right? Lumens or optical information, additional information other than lumens, okay? And then after numerous reflections, the radiation is dispersed highly uniformly at the sphere walls, often used to measure color metrics. So many times we'll put a luminaire onto the Gaudio photometer, but the color is a little bit more accurate with a sphere. So such as CCT, CRI, TM30, so forth, measurements that we talked about. But that's the second measurement. The sphere can do everything that the Gaudio photometer does. However, it sometimes gets to a matter of size. So this is a huge egg that opens up and may not house properly, depending if it's a large luminaire. Next thing we're going to talk about is spectral power distribution curve. So we saw this earlier in one part of the photometric report. You'll see it goes from 380 to 780 nanometers. That's 1/1000th of a meter. And the visual spectrum, so to the left of that is UV, and to the right of that is infrared and gamma rays and X-rays and so forth. So this is the visual part of the spectrum. And so that line that goes up and then back down, that is the spectral power of the various colors. So we call it a spectral power distribution curve. So as you go from left to right, you first see the purple, then the blue, then it goes to light blue, then to green. The green turns to yellow, the yellow turns to orange, the orange turns to red. Okay, so that's what a spectral power distribution curve looks like. And various light sources and with different CCTs look differently. And CRI, so each one is a little different. This is a typical LED. You have that blue spike to the left, and then you come all the way down, then you come up back on, and so forth. So the more red you have, the curve is going to be higher on the right side. Going to have more red, so it'll be higher. The warmer the light source, the lower that blue curve is. So here we are again. It's the same thing, except we also have a digital table. So here, right here is the peak, and here is the particular number. So it's 455 wavelength. That's in nanometers. Okay, and that gives us a 286. Okay, that's where we are. So we got tables as well as the curves for the values. Now we're going to switch gears again, and we're going to go into three things that you need to know that are kind of part of photometrics that you were going to run into when you deal with lighting photometrics. The first thing we're going to talk about is something called CIE classification. CIE is a French, stands for a French word that I can't pronounce over in France, but it has to do with the way the light comes out of the luminaire. So no matter what manufacturer it is, you've got various names that we'll uncover here and talk about. If you send this particular name, it includes this distribution. So the first one we have is what we call direct. So the light is coming down. But notice this. You see direct, it says 90 to 100%. So you can have as much as 10% uplight and it still qualifies as a direct luminaire. Okay, so you've got a little bit of option for uplight, even though the lighting is coming down. So then the next is semi-direct, 60 to 90 downward. So you've got more uplight. Then you've got direct, indirect. So it's equal. This is very popular distribution of schools back when in the days. I remember growing up in this. Fluorescent luminaires, direct, indirect, 50 up, 50 down. And then general diffuse. So this is omnidirectional light spreads in all directions, everywhere, right? So this is a official category. And then semi-indirect, so 60 to 90% upward. Very popular. So some of the later LED luminaires that are suspended, they'll send about 60% up and 40% down. It provides very comfortable, high quality light. And then the last one is indirect. We have a lot of indirect luminaires out there when most of the light goes up. So look at this, 90 to 100% of the output upward. So what that means is, hey, you can have 10% of the light coming down. And often when we went through the period, even today, whether it's in the home, where you have maybe a torchiere, or where you have another type of fixture, let's say a linear, in an office building that's suspended 18 inches from the ceiling. So we want to take the darkness off of the bottom of that fixture, so you could have as much 10% coming down, and it still qualifies totally for an indirect luminaire. Okay. Now, let's move to the second category that we want to talk about, and that's your NEMA beam spread classifications. Typically, you'll deal with NEMA beams when you talk about floodlights. And so the first thing we want to talk about is that the first number is always the horizontal angle. So how wide or narrow is that angle? And so a typical rating, when I say NEMA stands for National Electrical Manufacturers Association. So no matter who the manufacturer, if the light figures into these angles, then you can classify them as a NEMA 7x6 or 5x5 or whatever that angle is. So the first number is horizontal. So it's like this right here, it's spread, right? The horizontal angle. And the second one is the vertical angle, right? Up and down. So what is the vertical light angle? So a 7x6, you see 7 at the bottom there, you'll say 130 degrees and up. That means a very wide angle. Did you know that for floodlights, over 50% of the floodlights that are sold, stocked by distributors and sold in the country, are 7x6? Very popular, but not all. So you'll see over to the right and bottom these angles. So you have a range of angles. So for instance, if you look at a field angle of 46 to 70 degrees, that's the NEMA type 4. A NEMA type 4 is very popular to light flags. Typical 25, 30 foot mounting height. three lights around at 120 degrees is a typical way to light a flag. If you look at up at the top, a 18 to 29 degrees, that's more narrow. That's a spotlight. And even a 1 is 10 degrees to 18 degrees. So that's shooting a light a long distance. And so depending on what it is that you have, you can look at the numbers and kind of know how that light is going to come out of that luminaire. Okay. Now we have something here, again, just looking at these specifically, there's our 7, here's our 4, and here's our 1. And then we have something called a field angle. The field angle is really what we're talking about. And that's this angle up here at the top, not down lower where you see the beam angle, but the field angle is what we're measuring. Okay. So that's what that means. Now, so depending on what you have, you will know based on that floodlight what it is. You take a football field. You look up at the lights with the cluster up there and the tall poles, and you say, oh, all those fixtures are the same. Well, they look the same, but they all have different NEMA configurations. So to light the football field in the close to the first sideline, closest to you, you're going to have a wide angle floodlight. The one shooting further into the field, you're going to have a medium and sometimes a narrow floodlight to hit that part of the field. And so that's the way football fields are lighted with different NEMA configurations. Now let's move over to our distribution types for exterior lighting. This is like a parking lot. Okay, so the very first one is a type 1. We see this over in Europe, but really not in the US. It's very, very narrow. It was used and still used over there for trolley car tracks. A type 2 is in the US very popular to light pathways and 2-lane roads. And then type 3 is very common. Distributors stock this. This is the most common use. So the light goes a little further out sideways than it does crossways. Okay, so that's the 3. A 4 is just the opposite of that. So you've got a little bit more light going forward as far as the distance, more forward throw than you have side throw. And so that actually is the nickname of this light. A type 4 is a forward throw. You'll hear that. So you get that type 4. And then we have a type 5, which is symmetrical. And you'll see that's kind of like an oval, or really it's really a circle. Should be a circle because it's equidistant in all directions, 360 degrees around that pole. You've got the same amount of light, the same distribution. And then the last one is a 5S, which stands for square. So if you have a rectangular parking lot and you can get a type 5 symmetrical square distribution, then that's more efficient and better utilization of the light coming out of the luminaire. So that's what that means. Okay. So now we're going into the next section. So we've been preparing for this section the entire time. We're going to take all that we've learned and we use this information to do lighting calculations and other things too. But especially we mentioned that the files and information are used for lighting calculations. So there's different types of calculations. First category that we're going to talk about is something called average foot candles. Foot candles is the amount of light falling on a surface, and we take all these different points and we average them together. We got average foot candles. So the first method is the manual lumen method of estimator. Okay, so it's done with a hand calculator and more than one fixture type. You just add up the lumens. This is kind of like a guesstimate kind of thing. It's an estimator, makes it real simple, especially for people like in a home where you have layers of light. And let's just say you have a dining room. You want to get an idea, well, how much light is falling on the dining room table? And you may have an accent light. You may have a sconce. You may have a chandelier, and you may have a couple of downlights over the table. So all these different kinds. So, so this is a way that you can just add up the lumens, and we'll see this later. Next is our manual zonal cavity method, or lumen method. And you just take everything that we've been doing, the coefficient of utilization table, the light loss factors, and a lot of other things that we haven't really discussed, and you calculate it manually, just using a calculator. Or you can take this into an Excel spreadsheet, same lumen method. Our lighting calculator provides nice one-page printout. And so this is at the annual conference at ALA. I actually offered this to those who gave me their card, and I sent them a calculator. And I know some of you on the call have used that. And then that was free of charge, by the way. Lighting software program, web-based. So there are programs by manufacturers out there where you can actually pull in an IES file, and you can actually calculate, and it'll give you a diagram, and you use say the IES files. They're rectangular or square shaped rooms. It shows you a drawing, the spacing of the fixtures, and so forth, and does a nice little job really for and it's one level up in terms of accuracy. And then you have the full lighting design software, and it basically does it all. And we'll see some examples of this later. Okay, now let's go over from average foot candles to point foot candles. So how much light do I have at one point? Let's just say a particular point of reference is a portrait or a picture on a wall. How much lighting at one point? So the manual calculations, and the formulas that we use. There's three basic formulas that we use for that. Or there's the Excel spreadsheet. Again, I have a spreadsheet that I offered and sent out for doing this. And then you have your lighting design software, and such software suppliers as some of these are manufacturers. Some that come to mind are Visual, Light Pro, the independent one, the most popular, well-known in the U.S., that's most used by manufacturers as well as many other independent lighting designers, is AGI, by Lighting Analyst. And there's others also. So, and then a software often provides point-by-point layout. So each point, let's say on a parking lot or in an interior space, let's say an office building or could be a home, could be give you a foot candle value. Or you can also get a rendering, a graphical rendering of what the space looks like. And then it also calculates what we call uniformity ratios. This is very important for outdoor. It can be important for indoor, but very important for outdoor. And so we have something called the average demand and the max demand. So what does that mean? So average demand is of all the average points that you calculate, let's just say in a parking lot, that you come up with an average number compared to the lowest point in the parking lot, which we refer to as minimum. So you want to see what the average demand ratio is. So the wider or the bigger the ratio is, the worse the uniformity is, right? And if the smaller the ratio, then the more uniform the lighting is in that particular parking lot. And then the max demand is really the one that's really used the most in parking lots. And that is, what is your maximum point and what is your minimum point of light level? And by that, we can tell how uniform the overall space is. Okay, so now let's look at these in detail. Now that we just looked at this. So this is this very simple lumen method estimator. I showed you a book at the ALA conference that had this methodology inside the book. It was the lighting design book, version number 4. And so we're going to go through this. So although not as accurate, there is a more simplified way to estimate the amount of foot candles or lux in case of Europe, or in the number of luminaires needed in a room. So let's just say we solve for foot candles. So we divide the number of lumens generated by all the luminaires in a room by the area of the space. Of course, that's the length times the width. And again, I guess most popular feature of this is the fact that there can be more than one type of luminaire in a room. And you can also have more than one type luminaire in a room or in a parking lot with the full-blown design software. But again, you've got to remember this is just an estimate and so forth. But it's a nice feature where you've got layers of light, let's say, in a home. So you divide the result by 2 to obtain the approximate average light level foot candles in the room. This allows for all the factors that you calculate when you break it out either manually or with a spreadsheet. And you just basically say, okay, I'm just going to take half of that. That's just going to be my swag. And so the example here we're going to show you to see how we do this and how this works is have 800 square feet, and the average foot candle light level required is 50 foot candles in the room. So we have a luminaire that's 8 feet long. It's a direct indirect LED pendant, and it's 1,300 lumens per linear foot. So this is a harder one because you've got to deal with luminaires and linear stuff and so forth, but it works just the same for just an individual fixture. So you run that formula that we just talked about, and you got 8 luminaires. So here's the math. Okay, so you got 1,300 lumens per linear foot times an 8-foot fixture times 8 fixtures divided by the square footage. And that gives us 104. And then we divide 104 by 2. And guess what? We've got 52 foot candles, average maintained. Everybody can use this little formula, this little cheat sheet, and do this. Okay, so now what do we want to solve for number of luminaires? So multiply the desired average maintained light level by 2. Multiply the result by the area in the room, length times the width. Divide the number of lumens in the room by the rated lumens of the LED luminaire. And then the example we're going to do is kind of the inverse, where we've got 50 foot candles. The area is 800 square feet. That's the length times the width. The fixture is 8 feet long. We just saw that it was a direct, indirect, and we've got 1,300 lumens per linear foot. So doing the math, you got 50 times 2 is 100. 100 times 800 equals 80,000. 80,000 divided by 1,300 lumens per foot times 8-foot luminaire, and we get 80,000 divided by 10,400 or 8 luminaires. That's the way it's done. So now, what are the concerns with this simple method, right? So you've got some rules we got to follow. So first of all, use it for ordinary spaces with white ceilings, medium to light walls, and reasonable number of windows. So if anything is extreme in your space, it's probably not going to work. So especially like dark colored walls, unusual shapes, that sort of thing. This is kind of like your typical room. Then use common everyday lighting equipment. Avoid custom designs and clever uses of lighting. So if you've got some really hippy-dippy, unusual, cool fixture or something that has unusual distributions, probably not going to work too well either. Maybe it's custom design, whatever. Okay, and then understand that the different effects of point sources and ambient sources. Do you have a really narrow spotlight? Do you have a wide distribution light? We're just looking for just like common type applications. Things that are unusual will skew your results a little bit. And the lumen ratings are for LED fixtures. Okay. So for traditional light sources, you can back this out and you have to use this luminaire efficiency factor. So what you have to do is you have to account for the light that's trapped. Okay, and do that. So, but today, most everything is LED, so you're probably not going to run into that. Okay, now this is the spreadsheet programs that I mentioned. These are mine. I wrote them. I have had third-party verification, and this is what I offered at ALA. And some of you already have these. So this solves for the number of fixtures, uh, basically, and so that you need. So you have 50-foot candles, and you got your 10 by 15 and so forth, and it goes down here, and you do have to have a coefficient of utilization table. And by the way, when I actually included this in the tool, I give you a little cheat sheet over on the right. So this is something I added since I did this slide. It don't show this because it tells you and reminds you, okay, here's what you need to put in this block. Here's what you need to put in the next block. Kind of explains each one step by step. Makes it really easy. So you know what? If we don't do this every day, we're probably not up on it. So we need a little reminder. So that's what this is. So what it does is it calculates the RCR for you. In this case, it's 5. So you go up, take the CU table that is on your specification sheet for that luminaire, and you say, okay, based on this, my value is somewhere between 4 and 5. May have to interpolate, so it's going to do that. And so the interpolated value in this case is 0.5. It goes up into the formula. Bingo, you got four luminaires, and the recalculated value with rounding gets you to 41 foot candles. Pretty simple. Over on the right is the light loss factors. So this sometimes gets into a little bit more for the commercial side, but basically it's real simple. So what kind of light losses do you have? You have something called recoverable factors, which means if I clean the luminaire, that's luminaire dirt depreciation. So you can recover. Lamp, you can put your lamp in, you can recover. And then your non-recoverable factors are things that if you put a brand new item in, it's not going to be any change. So for instance, the ballast factor is the ballast factor, where it's 5 years old or brand new. This luminaire surface depreciation really doesn't change. The ambient temperature, so forth and so on. So you have a total light loss factor. All you have to do is just plug in a value there. If you don't know a value, then what I'd suggest is just putting a lamp lumen depreciation of 0.9 and putting 1.0 in all the other fields or cells, and use a 0.9 for your total light loss factor, which is typical for LED luminaires. Okay, so we got our 50, we got our 4, we got our 41, which rounds it back up, takes us to that. Then we calculate for the lumen method using, they have the 4 luminaires. How many foot candles do we have? In this case, so we have foot candles, we have 42 foot candles. And so there's some differences here that we arrived. So before we had 41 foot candles for 4 luminaires. So just a little bit of a variation depending on the rounding. Same thing over on the right. Okay. 4 luminaires gives us 42 foot candles. Okay, now the next category of calculations is the free lighting software from on the websites. And here's an example from one that we see over here on the right. This one is written by lighting analyst, and it puts the particular company name on the logo. So this is free. So here's some people that have this kind of thing, just some manufacturers that have it. There's others that have it as well. You can check to see if they have it offered as a free service, online calculations. If they do and it works for you, it's great. If you have a box and you want to know or a square, want to know how much light you need or how many luminaires that you need, works great. And so this is a summary. You have 45 foot candles. You need 12 luminaires. And this is the watts per square foot of 0.4. And then this is the graphical use interface that you get for the layout. All right, now then we have the full-blown software calculation programs. AGI Dialux is free. It's a download, very popular in Europe. So you use some in this country. And it's a little different format, but it does the same thing as AGI does, basically. Maybe not all the features, but it's a full-blown software. And then you have others. And so the manufacturers, which if you qualify for, it's free. Some of those manufacturers are online as well. So it just depends, you contact those. And so now we're looking at some renderings. So over on the left, you see a black and white rendering of what that space would look like lighted there. And then you have the color rendering with the point by point on the graphical interface there, the layout, and also the colors. And then those lines, that lime colored line, light green, that is called an ISO foot candle distribution curve. So it's just like everywhere that you see on that line is a certain amount of foot candles, as opposed to just a point digital value, what that is. And this is AGI, where you have the point by point in a parking lot. So this is what a point by point layout would look like for a parking lot. And you see the ISO curves in red, and you see the values and foot candles in white with the numbers. And then last, we're going into point calculations, and this is my third calculator that I offered. And so first of all, you see one where it's perpendicular, so the particular luminaire goes straight down to the table. So you want to know how much light is directly below the luminaire for the where I'm reading or where I'm working. So that's the first calculation. The second calculation is where your task is to the side. It's horizontal, but it's not straight down right over the task. And then the third version is where you have a vertical surface like a picture on a wall, and you want to know maybe I've got a monopoint on a ceiling or maybe some track lighting, and you want to know if I come up from vertical, you see that angle right there? It comes up from the bottom, from nadir, straight down. Okay, it comes up, so the angle is coming up. So if it's 30 degrees up, then that's the way we look at that. And so let's just look at this, how this works. So you've got a value from your particular lamp or fixture that you're using, and let's say the center beam candle power, right in the center of that particular floodlight or spotlight, you have a rating in the catalog or on the cut sheet. It says 30,000. Let's see, this is 10,000. Okay, so 10,000 is the candle power at the center beam of the candle power. The next one is the distance from the lamp luminaire to the task. That's from the light fixture, from the track fixture to the picture. And then the next one is the angle that we talked about here, coming from nadir up, the aiming angle that you're doing. So you use this formula or spreadsheet, bingo. This is so simple. And this is viewed by many people as being really difficult to do because you don't do it every day. It's hard. So easy to just pull out this little tool and make that calculation so you'll know what it is. And we go into some other things such as, well, how much light do I need on a wall for a picture? And so for a home, the amount of light on a picture needs to be 3 times brighter than the immediate surround. So for a commercial, it's probably 5 to 10 times, but for home lighting, it's typically 3 times brighter. So therefore, depending on what you need. So if you have 10 foot candles in a room for your general lighting for a home, then 3 times that would be 30. So this would be maybe.
I'm still here.
Okay, good. Do you have any questions?
Well, so when you were showing like calculating for the foot candles and you had said this is great, like if you have a box, a square or rectangle. I do a lot of homes with tall vaulted ceilings. One recently we ended up not doing any recessed on, and they didn't want cylinders. And this was a 24-foot peak and the pitch was 1612. So hard to light.
Hard to lie.
Current, yeah. So currently I have another one where I want to say we got a 17-foot peak, and it's more of a normal angle. I think we're around probably 12, you know. Um, but how are you calculating when you have to mount lights at different mounting heights from the floor or the task area on a ceiling like that? Would you just kind of do an average?
Well, it comes back to the same thing that we have to kind of figure. So the answer is no. You wouldn't want to. Excuse me. Would not want to do an average. So what you have to do, you have your particular lamp that you want to try, or a particular fixture with a certain center beam candle power. That's given, right? So then you go and say, what is my distance from that fixture, wherever that's mounted? It could be mounted on the ceiling or wherever, because you've got different pitches and so forth, depending on what you're using. What is the distance from there to the object that you're lighting? And I'm assuming that's a vertical wall, item on a vertical wall. Is that correct?
Currently I'm just talking about like the room itself.
Oh,
I'm just talking about general lighting. Yeah, I wasn't talking about
well,
like lighting
okay.
an object.
So that doesn't apply to point source lighting. So what that is you're lighting at an angle. So you use a wide angle type luminaires, and it depends on what you can light. So are you going to be using a track since you have a sloped ceiling, or what are you going to be using?
Um, a adjustable recessed.
Oh, okay, adjustable recess. Okay.
Mhm.
Well, so you got a photometric file. So can you aim the luminaires so it's adjustable? Can all of them point down?
They can.
Okay. So what you've got is you've got you've got a sloped ceiling. That's a difficult calculation. Uh, so
So that's why I was asking if you would just take an average, like because if we're not, like it's not a commercial project, but we just want to make sure that we're lighting enough for the space. And I know like we really only need in this area 10 to 20 foot candles.
mhm.
Um, so that's what I was trying to like figure out. Like, is it working per fixture or
My idea for lighting that space, first of all, is your ceiling vaulted, so with wood, nice, beautiful wood.
yes.
So you won't have some uplight on the particular wood, first of all. So
Mm-hmm.
you want to display that in the ambiance as well. You want to have some uplight as well as some downlight. So that's the first thing. Then you got I would use table lamps. I would use accent lighting and maybe some sconces. And then you go to need a few downlights for your task lights. So you've
Mm-hmm.
got probably that room, if it's high end residential, you probably got 4 layers of light to use.
Yeah.
And then
Mm-hmm.
what you do is you put them on dimmers, and you're not going to lose. Really, I mean, because every person that comes in there. So let's say the husband comes in and they want to do one thing right now tonight, and they want certain mood, and then maybe the wife comes in and she's doing something totally different. Maybe she wants to watch TV, and earlier the husband was in there and he was maybe working or something, or vice versa. Um, so the adjustment, being able to adjust the different layers is it's a good idea for you, because then they can come back to you. And if you don't put dimmers on, you want to utilize fixtures that are dimmable. Now,
Right.
the non-dim fixtures are less expensive, but I wouldn't do it. I would. So if you could do it, you could put it in later possibly, but I would use dimming on the fixtures. So,
Most of the homes that we work on have an AV contractor that's doing the entire house.
good.
Um,
Okay.
control 4 or, you know, whatever they're using now. I can't remember the name of it.
So
Um,
three or four layers of light. You got uplight. You've got table lamps. Those can be on off. Maybe a torchiere. If you use a torchiere, I would also. I don't like all uplight. I like translucent bottom globe as well as uplight
mhm.
because you have nice soft vertical light. And so if you use those, that would be what I would suggest. And then you've got your maybe a sconce or two placed strategically here and there, and then you've got your some downlighting to fill in the spaces where you couldn't hit with some of the other things.
Right.
That help?
All right. Yep, that helps. Thank you.
Okay. Well, thanks for tuning in.